Alright, gang, here we go. This is for Chem 1, Unit 7, Part 3. We're predicting products. Now, the trick to this is it can actually be kind of tricky. It takes a lot of the things that we've learned. I've been telling you all year that chemistry builds on itself as you continually go. You're building, and everything is just kind of coalesces. And this is one of those times where everything you've learned, a lot of the things you've learned, are kind of coming together all at once. Okay, so just to recap, last couple of parts we talked about balancing chemical equations, and then we talked about types of chemical equations. All right. So remember, there were 5 basic types of chemical equations. If you don't remember what those are, go back and watch the previous unit, or take a second and look at your notes, because you need to be able to recognize the 5 types of chemical equations that we talk about in class in order to do this part. You'll also notice that I provide you a lot of practice problems on these. I'm going to do 6 example problems in the video. Okay, but there's a ton of practice. I highly suggest you work through all of the practice and check your work, okay, because the only way to get good at doing this is just by doing a ton of them. Okay, and that's just the fact of the matter. There are certain tricks to look for, and but you really only get good at it by practice. All right. So first thing whenever you're predicting products is you want to look for what type of chemical reaction you're looking at. Now this case here, you're starting with one thing that's combined. Okay, it's just one thing, and there was only one type of chemical reaction where we started with just one thing, and that was the decomposition reaction. So we'll go ahead and label this as decomposition. Okay, so that means this thing is going to break down into its substituents. All right, so aluminum is going to turn into just aluminum, right? And we know that aluminum is a solid at room temperature, so we'll just throw that in there. And then the oxygen is going to turn into oxygen, and oxygen is a diatomic element. Okay, and so that's a gas, and we know that from our knowledge of elemental states of matter. Okay, and so these are the two things that aluminum oxide will break down into, aluminum solid and oxygen gas. Okay, we could also balance this, so we've got a 2 here, so we'll throw a 2 in front of that aluminum, and then we've got a 3 here and a 2 here, so that means we need a 3 here, and then a 2 here, and that's going to change our aluminum, and so that would make this a 4 to make that all balanced, as all things should be. All right, so anyway, now you might be asking yourself, wait, Mr. McLeod got rid of this 2 that was right here. Notice that there's a 2 on this aluminum and a 3 on this oxygen, and I changed them over here. Now the trick is when the elements are by themselves, you want to completely ignore what these subscripts are when you're predicting the products. Now, if you're messing around with a polyatomic, life gets more interesting and you have to pay attention to them. All right, so on this next one, for example, okay, it's going to be slightly different. So we've got this new example here, magnesium sulfate and sodium chloride, and we want to figure out what the products are. Now what you need to do, we need to decide which of the 5 types it is. Well, we know for sure it's not decomposition because we're starting with 2 things. We also know that it can't be synthesis because it's not 2 simple things combined. There's 2 complex things. We got magnesium and a sulfate and a sodium and a chloride. So that should tell you right away that we should be looking at a double replacement reaction. Okay. Now, another way to check is to try to break these things up into a cation and an anion. All right, magnesium is a cation, so this would be plus, and then sulfate is an anion, and so that would be your minus. Notice we have a positive part of this one and a negative part of this one. Okay, 2 distinct ions get formed. Same thing here. Sodium is a positive cation, it's metal, and then chlorine is your anion. Notice that we've got these 2 parts. This looks just like our double replacement reaction where we had 2 things combined, or A with X and B with Y, and then what happens when we put these together? Well, they do the do-si-do, right? And if you've ever been square dancing, double replacement, okay. So they do the do-si-do, and the pluses go with the negative from the other, and they flip partners, right? So the magnesium is going to go with the chlorine. Now this is where things get really exciting. We have to think about charges here. So you have to pull out your periodic table. Okay, what's the charge on a magnesium? Well, the charge on a magnesium is 2 plus, right? So I'm just going to jot down a 2 plus right there. And the charge on a chlorine is a 1 minus, okay? So we got a crisscross. So we're going to bring that 2 down here, okay? And then bring the 1 down there for the magnesium, okay? And then we'll cross this guy out so that we get magnesium chloride, all right? So this would be actually the product that it makes, all right? And then the other one here is we've got sodium sulfate, right? Because we already used the plus here for this magnesium with this chlorine. So now we're going to put the sodium with the sulfate. So we get NaBr, with SO4. Now we have to think about the charges again. Sodium is an alkali metal. It's in the first column of the periodic table, so we got a plus. And sulfate is a polyatomic ion, so you can look at your cheat sheet to figure out it's 2 minus. Okay. The other thing you could do to make sure to, like, if you're like, oh, I forgot my cheat sheet and I don't remember what sulfate is, we can also look at this over here. We know that magnesium has a charge of 2 plus, and sulfate's right here. And if it's in a 1-to-1 ratio, that means our sulfate had to have been 2 minus to cancel the 2 plus from the magnesium. Pretty slick. All right, so then we crisscross that, so we'll bring the 2 down here for that sodium, the 1 down for the sulfate. We're good, and we'll just cross that out because that doesn't mean anything anymore. All right, now for funsies, we'll just go ahead and balance this thing. So we got 1 magnesium, 1 magnesium. All right, for these guys, for polyatomics, I just treat them as one giant thing, right? So this is 1 sulfate, and we have 1 sulfate over here. Notice that I'm not treating it as just a sulfur and oxygen. I'm treating it as the entire polyatomic ion. It makes balancing it a lot easier. All right, so that's sulfate and sulfate. All right, sodium here, we've got 1 sodium. Oh no, we've got 2 sodium, so we need to put a 2 in front of this guy. All right, now we check our chlorines. Right now we've got 2 chlorines over here, 2 chlorines over here, so now we're balanced. All right, so 1, 2, 1, 1 would be the coefficients. All right, next one here, you should recognize right away that this guy here is exactly like this one. We've got a positive and a minus and a positive and a minus setup. So this is also going to be a double replacement. Okay, and we're going to do the do-si-do. The calcium is going to go with the bromine, but we got to think about our charges. Okay, charge on a calcium is 2 plus. It's an alkaline earth metal, right? It's right underneath magnesium, so we'll throw that 2 plus up here just to remind ourselves. Bromine is a halogen, so it has a charge of -1. All right, then we do the crisscross. All right, we bring the 2 down here. All right, and the 1 goes over the calcium. We'll cross those out because we don't need them anymore. All right, so those are our calcium bromide. All right, and then for the next one, we're going to combine the nickel with the oxygen. All right, so we got the nickel, okay, and the oxygen. Now, this one's a little bit more complicated. We got to think about our charges here. Now, nickel is a transition metal. And remember, transition metals can change their charges. So the only way to determine what the charge on that nickel would be is by looking at what it was attached to over here. There's 3 bromines. Each bromine is -1. So that means our nickel had to have been 3 plus. All right, let's go over that again. There are 3 bromines. Each one of them is -1, and we had 1 nickel to balance out all of these bromines. So that means the nickel had to have been 3 plus. So we put that 3 plus over here. Oxygen is 2 minus right next to the halogens. All right, so we're going to crisscross. The 3 goes with the oxygen, 2 goes with the nickel, and you're good to go. And so that's your equation here. We'll go ahead and balance this. So calcium, 1 calcium, 1 calcium, oxygen, and then 3 oxygen. So we'll put a 3 over here. Okay, but that changes our calcium now, right? So because now we have 3 calcium, so we got to throw that 3 up there. All right, and then we go to nickels. So we got 1 nickel, 2 nickels, so we'll throw a 2 in front of that guy. And then, so now we've got 6 bromines and 6 bromines. We're good to go. All right, so there's our balanced chemical equation with the predicted products. All right, a couple more. All right, so here's C2H6, ethane, mixing with oxygen. All right, so you should see right away that we've got a hydrocarbon. Remember, a hydrocarbon is anytime you've got a hydrogen and carbon combined. So this is our hydrocarbon. So this is a combustion reaction, combustion. And remember, this is really nice. Whenever we see combustion, it's easy because we always make the same 2 products. We're going to make carbon dioxide and water. Carbon dioxide and water. Okay. So predicting products is really easy for these guys. Balancing them can be a pain in the neck, though, so let's give it a shot. So we got 2 carbons, 1 carbon, so we'll throw a 2 out there like that. We've got 6 hydrogens, 2 hydrogens, so we'll throw a 3 in front of that guy. Now we got to check our oxygens. This is really where we get stuck in the mire. We've got 2 oxygens here. On this side, we've got 4 oxygens from this, right? 2 CO2s, and we've got 3 oxygens here. So that's 7, so we're going to have 7 halves of an oxygen. Yeah. Now remember, I told you we can throw that 7 halves in there, but then we can't leave it forever. We got to change it. All right. And so in order to change it, we're simply going to multiply this whole thing by 2. So all of these coefficients are going to get multiplied by 2. All right. So we get, so this was a 1, so it'll become a 2. This was 7 halves, so it'll become 7. All right. This was a 2, so now it'll become 4. And this was a 3, so now it'll become 6. And we should be balanced. We'll just double check this. 2 carbons, 2 to 4 carbons. okay, 4 carbons, and then 14 oxygens, okay, and 1, 2, 3, 4, 5, 6, 7, 8 right here, plus 6, that's 14. We're all balanced. Good to go. All right. This next one, okay, might look like a double replacement like we've done so far, but it's not quite a double replacement because look, this potassium is not attached to anything at all to start. Remember, so this has to be a single replacement reaction because that potassium is all by itself. Single replacement, right? So whenever we look at single replacement reactions, we always have to look at our activity series. So remember this activity series, we had to look back, and in a single replacement reaction, it only occurs if the metal that's by itself is more reactive than the metal that's attached to the nonmetal originally. So we've got potassium, okay, and then the other one was aluminum. So we got to look at potassium and aluminum here. So we find aluminum, aluminum's right here, and then we find potassium, it's up here. Potassium is much more reactive than aluminum, so we will have a reaction. That's nice, okay? And all that happens is that they change places, right? So the aluminum gets to be by itself like that, and then the potassium is going to be attached to the chlorine. So, and then we got to think about the charges, all right? So potassium is an alkali metal. It's got a charge of +1. Okay, or 1 plus, excuse me, and then chlorine is a halogen, so it's -1. Okay, so it's 1 to 1, so it's just like that. All right, then to balance it, we got 1 potassium, 1 potassium, 1 aluminum, 1 aluminum. Now the chlorines, we got 3 chlorines here, but only 1 chlorine here, so we'll throw 3 in front, but that changes our potassium, so we'll have to throw that 3 in front of that potassium. And that's it. That's your balanced chemical equation for potassium replacing the aluminum. All right, and the last one here, so this would have to be a synthesis reaction. All right. Now, why do you think it has to be synthesis? Well, we've got 2 elements that are combining, right? They're not attached to anything else. They're just chilling. So they're going to take these 2 things, combine them together, so we get S, R, and N. And we got to think about the charges here. Okay. So strontium is an alkaline earth metal, so it has a charge of 2+. Okay. Nitrogen is a nonmetal. It's over there. It's in that group next to oxygen, so it's going to be 3-. Okay, we crisscross, so the 3 comes down here for the strontium, 2 comes down here for the nitrogen. Good to go. Now we're just going to balance it, so we're going to put a 3 here for that strontium. Nitrogen's 2 nitrogens, you're done. Okay, so we did one example of each of them, how to kind of identify what type of chemical equation that was, and then be able to predict the products. Right? Do lots and lots and lots and lots of practice problems. Check your work, making sure you're doing it right. If you have any questions, come and see me, and I'll see you on the flip side.